Welcome to Naradar Academy. In this video, we are going to discuss about basis and dimension of a vector space. So let us start with span of a set. Suppose S is a non-empty subset of a vector space V, then the set of all linear combinations of elements of S is called linear span and it is denoted by L of S. That is, if we have V1, V2, etc. Vn as elements of S, then L of S will contain the linear combinations of the form alpha 1 V1 plus alpha 2 V2 plus etc. alpha n Vn, where these alphas are taken from the field. Okay, they are scalars. Okay, so span is nothing but linear combination of vectors and scalars. Okay, this is called span of a set. Let's see some important results about span. Now, this L of S is no. L of S is a subspace of V. Okay, what do you mean by a subspace? That is, any subset of a vector space which itself is a vector space is called a subspace. So, this L of S is always a subspace of V. And this is another important remark. S is a subset of L of S. That is, L of S is the smallest subspace. Okay, smallest subspace of V which contains S. Okay, right. Then the next one is, let V be a vector space over a field F and S and T be subspaces of V. Then if S is contained in T, then L of S is contained in L of T. And L of S union T equal to L of S plus L of T. And L of S is equal to S if and only if S is a subspace of V. So in the previous remark, we have seen that yes, L of S is the smallest subspace of V containing S. Now we are claiming L of S is equal to S. When this is possible? Only when S is a subspace of V. So when you have S as a subspace of V, then L of S will become equal to S. Okay. So these are the important results that we have to remember for span of a set. Then the next one is linear independence. Linearly independent set of vector means, suppose if we take n vectors from a vector space, take their linear combination equal to 0. That is alpha 1 v1 plus alpha 2 v2 plus etc. alpha n vn equal to 0. If the linear combination of the vectors equal to 0 implies the scalars alpha 1, alpha 2, all the scalars are equal to 0, then the set of vectors are said to be linearly independent. If any one of them is non-zero, then the vectors are said to be dependent. Okay, right. So we have seen what is a span of a set and what do you mean by linearly independent set. Okay, now let's see some important results about linear independence. Any subset of a linearly independent set is linearly independent and any superset of a linearly dependent set is linearly dependent. These two are also important. See, suppose if you take a linearly independent set, whatever subset you take from that one, that will also become linearly independent. Okay, so the original set is linearly independent. So all its subsets are also linearly independent. On the other way, you take one linearly dependent set. Okay, you take one linearly dependent set. With that linearly dependent set, you write some larger set, that is superset for this set. Okay, that will obviously become a linearly dependent set. So any set containing linearly dependent set will become linearly dependent. So if you want to check whether a given set is linearly dependent or not, you need not to check with all the vectors. Okay, you search for at least one or two vectors, sorry, not one or two, two or three vectors which are linearly dependent. If they are linearly dependent, the entire set can be concluded as linearly dependent. Okay, right. These are used for simplifying the calculation. That is why I said they are important. Okay, right. Next one is, let S be a linearly independent set of vectors over a field F. Then every element of L of S can be uniquely written in the form alpha 1 v1, alpha 2 v2 plus etc. alpha n vn, where alphas are scalars. So what do you mean by this statement? See, already we have seen what is a span. Span means what? Linear combination of vectors. But linear combination of vectors may be unique or need not be, isn't it? When will they become unique? When will they have a unique representation of linear combination? For that one, we need the condition that the vectors should be linearly independent. Okay, that is, when you take a set of linearly independent vectors, then when whatever linear combination you write with these set of vectors, the representation will be what? Unique. They will give you unique vectors. Okay, otherwise they need not to give you the unique vectors. They may give you the same vectors repeatedly. So for getting unique vectors, unique linear combination of vectors, you must have the set to be linearly independent. Okay, right. Next one. Suppose if we have a linearly dependent set. Okay, linearly dependent set. So what do you mean by that one? That means linearly dependent means at least one of the vectors here in the set itself, one of the vectors should be linear combination of the others. Okay, right? One of the vectors will be linear combination of the other vectors. That is what we are saying here. Okay, right. Then next one, let us come to basis and dimension of vector spaces. See, a vector space V over a field F is said to be finite dimensional if there exists a finite subset of V for which L of S is equal to V. That means we have a finite set which spans. What do you mean by L of S? Spanning set, no? L of S is equal to V. If we get L of S equal to V for finite subset S, then what do we say? The vector space is finite dimensional, right? Then what is a basis? A linearly independent set which also spans the whole space is called a basis. That is, if you have a vector space, okay, that vector space is spanned by a subset which is also linearly independent, that is called a basis. So for basis we need both the things, linearly independent and span the whole space. Both the conditions are required for a set to be a basis for the given vector space. Then the next one, let V be a finite dimensional vector space over a field F. Then the number of elements in any basis of V is called the dimension. Okay, first we have defined what is basis and we have defined what is dimension. Dimension means nothing but number of elements in the basis. Okay, so what if you have two or more bases for a given vector space? They must all be same. That means if for a given vector space you find two or more bases, okay, two or more set of basis elements, then in that case the number of elements in each basis should be equal. Okay, right? So that will represent the dimension of the vector space. Okay, next one, we are correlating the dimension with linear dependency and spanning. See, suppose if we take one vector space of dimension n, okay, that means what? In the basis there are n vectors, isn't it? Okay, if you take any set of m vectors for m greater than n, that is n vectors are there in the basis, no? If you take any set containing more than n, that will become linearly dependent. If one element is extra added, that will become what? Linearly dependent, because the basis itself is having only n elements. And if you lose one of the elements, at least one of the elements, if you drop from here this set, that will not span V. Okay, that means what? With the basis, if you add basis, there are n elements, no? With that n elements, if you have even one element extra, that will become linearly dependent. If you drop at least one of the elements, that will not span. So this we call it as maximal linearly independent set and minimal generating set. The basis is there, no? The basis is called what? Maximal linearly independent set and minimal generating set. Okay, right. Then the next one, any vector space of dimension n over a field F is isomorphic to Vn of F. So here we are talking about isomorphism of finite dimensional and any other dimension. Okay, so if it is of dimension n over a field F, then it must be isomorphic to vector space of dimension n over field F. And any two vector space of same dimension over a field F, field is also same, dimension is also same. That means those two vector spaces are isomorphic. Okay, then next one, here we are going to combine the dimension with the linear transformation. See, I have two vector spaces V and W, and I have a isomorphism from V to W. T is isomorphism. What do you mean by isomorphism? It's a linear transformation along with 1 1 on 2 condition, isn't it? So if I take isomorphism from V onto W, then the elements of the basis here both are vector spaces, no? So you will be having basis for both the vector spaces. The basis of this vector space will be mapped onto the basis of the other vector space. So otherwise we can say a linear transformation is completely determined by its values on the elements of basis. So if you want to identify linear transformation on a vector space, it is enough if you find the value of the linear transformation only on the basis. That will give you the entire picture of the linear transformation. Okay, right. Then let V be a finite dimensional vector space over a field F and W be a subspace of V. Then that is any subspace, dimension of any subspace is less than or equal to dimension of the original space, and dimension of the quotient space V by W is equal to dimension of V minus dimension of W. And suppose if V is a vector space and A and B are subspaces of V, then dimension of A plus B is given by dimension of A plus dimension of B minus dimension of A intersection B. Suppose if V equal to direct sum of A and B, in that case this will become what? 0, because if you write V as a direct sum of A and B, A intersection B will be what? Singleton set 0. Singleton 0 means dimension is also 0. Therefore, simply we have dimension of A plus B equal to dimension of A plus dimension of B. Okay, right. Now let's see some problems. First, let's see a set of problems for span of a set, then for linear independence, and then for basis and dimension. Okay, right. First, find the span of the set S is equal to 1 0 0 0 1 0 0 0 1 in V3 of R. So, while finding the span of the set, you have to be very careful in which set they are defining, because that plays an important role. So that you have to choose alphas, that is the scalars accordingly. So here V3 of R means what? Vector space over the field R. So let me take 3 scalars from R. Alpha, beta, gamma belongs to R. L of S means what? Alpha into E1 plus beta into E2 plus gamma into E3. That is the linear combination, where this alpha, beta, gamma belongs to R. That is, these vectors are E1, E2, E3 are fixed here. Okay, this alpha, beta, gamma are varying numbers. They will take different values from R. Okay, so these are the small things that you have to remember, which will characterize the set. Okay, right. Now here you see alpha into 1 0 0 means what? Alpha 0 0 0 plus beta into means what? 0 beta 0 plus gamma into this one means what? 0 0 gamma. So if you add all these things together, you will be getting what? Alpha, beta, gamma, where alpha, beta, gamma varies over real numbers. Okay, that means this is equal to V3 of R. So see, this plays an important role. Alpha, beta, gamma belongs to R. That means for different, that is whenever this alpha, beta, gamma take different values on R, different elements are generated in L of S. Therefore, it will generate the entire V3 of R. Okay, right. Then next problem. Find the span of S equal to 1 0 0 2 0 0 3 0 0 in again in V3 of R I have given. See, so you have to put what? Alpha into first vector plus beta into second vector plus gamma into third vector. Okay, let me look at the second and third components. Both are 0 in all the 3 vectors. So second and third coordinates are 0. What about the first coordinate? Alpha plus 2 beta plus 3 gamma, isn't it? Alpha plus 2 beta plus 3 gamma, where this alpha, beta, gamma varies over R. Okay, so in general, how can I write? X, set of all x 0 0, where x belongs to R. By that is, actually I am getting it as alpha plus 2 beta plus 3 gamma. By varying the values of alpha, beta, gamma, you will get the entire set of what? Entire set of points in the x-axis. Okay, right? So this will generate, this set will generate the collection of all points in the x-axis. Next one, find the span of S is equal to 1, 2, 3 in Z5 cross Z5 cross Z5 over Z5. Okay, so see, whenever you see this one, you have to be very careful with over which vector space and over which field they are asking you. That is important, because depending on the field only you will get the answer. Okay, right. Now over the field, what? Z5. Z5 means what? Additive modulo group 5. That means it contains only elements 0, 1, 2, 3 and 4, isn't it? Okay, right. So L of S will be alpha into only single element is there, no? Alpha into 1, 2, 3 means what? Set of all alpha, 2 alpha, 3 alpha, where alpha takes the value from the field. What is the field given here? Z5. What are the elements of Z5? 0, 1, 2, 3, 4. Okay, so only these 4 different elements this alpha can assume. Okay, so this point is very important. Now you substitute. Only 4 elements are there, no? You substitute the values and let us find out. So first if you substitute 0, 0, 0, 0. For alpha equal to 1, it will be 1, 2, 3. For alpha equal to 2, it will be 2, 4 and 3 2s are 6, no? But we are defining over Z5. Additive modulo 5. So 6 means what? 6 minus 5 equal to 1. Okay, right. Next one. Next one, what we have to give? Alpha equal to 3. For alpha equal to 3, the first element is 3, the second element is 6. 6 we cannot write, isn't it? Because the field contains only the elements from 0 to 4. So 6 means what? 6 minus 5 equal to 1. Then the third element is 3 3s are 9. So 9 you should not write. Instead of 9, what should you write? 4. Okay, right, okay. Next one, for alpha equal to 4, it will be 4 comma 8. But 8 is equal to 3 in Z5, isn't it? And then 3 4s are 12. 12 means what? It's equal to 2 in Z5. So this is the span of the set generated by 1, 2, 3 in Z5, Z5, Z5. Understand? Okay. Next one more similar example we will see. Here we have few more elements. Find the span of the set S equal to 0, 1, 2, 1, 2, 0 in Z3, Z3 cross Z3 over Z3. So what is Z3? It is containing the elements only 0, 1 and 2. Okay, so let us take, here only 2 elements are given, no? Let me take only alpha and beta from Z3, not Z5, Z3. Okay, so let me write it in the form of table so that I can write easily. Here on this side I have taken one of the vectors 0, 1, 2 and this side I have taken 1, 2, 0. Okay, so these are the alphas and betas, no? So here I have written this alpha's value. This is alpha. Okay, 0, 1, 2. So let me multiply alpha into 0, 1, 2, 0, 0, 0. 1 into 0, 1, 2, 0, 1, 2. 2 into 0, 1, 2, 0, 2, 4. But 4 I should not write because it is Z3 group, no? It will be 1. And similarly, here you have to write beta values. Beta will be again what? 0, 1, 2. Okay, so now you write this vector into beta. This vector into 0, 0. This vector into 1, the same vector. This vector into 2, it will become 2. 2 2s are 4. 4 will become 1 and 0 into 2, 0. Now for linear combination, what you have to do? Alpha into first vector plus beta into second vector. That is, you have to add these two vectors. Let me add here itself. So it will be easy for me if I put it in the form of table. Okay, so you add 0, 0, 0. So this entire row will become 1, 2, 0, 2, 1, 0. And similarly here also, since this is 0, 0, 0, no. So this column will come as it is. Now let us see this one. 0 plus 1, 1. 1 plus 2, 3. But 3 you should not write, no. So instead of 3 you have to put what? 0. Because it is Z3 space, no. 0. Next one is 2 plus 0. 2 plus 0 is 2. Next one is 0 plus 2 is 2. And 1 plus 1 is 2 and 2 plus 0 is 2. Next one, 0 plus 1 is 3. Sorry, 0 plus 1 is 1 and 2 plus 2 is 4. 4 instead of 4 you should write 1 and 1 plus 0 is 1. Next one, 0 plus 2 is 2 and 2 plus 1 is 3. Instead of 3 I put 0 and 1 plus 0 is 1. So these are the 9 elements which are generated by the set. Okay, right? Here it is 0. So these are the 9 elements which are obtained from the span of the set. Okay, right. Next one, find the span of S is equal to matrices of the form 1 0 0 0 0 0 1 0 in M2 of R. What do you mean by M2 of R? Set of all 2 by 2 matrices over the field R. Okay, so you have to put alpha into the first matrix plus beta into the second matrix. So what will you get? Alpha 0, beta 0. Okay, where this alpha and betas varies over R. So instead of alpha beta, let me write it as xy. So this will generate the matrices of the form x0, y0, where x and y are real numbers. Okay, right. Then next problem. Find the span of the set 1x, x square, etc. up to x power n in R of x. What do you mean by R of x? Set of all polynomials over the field of real numbers. Okay. That means you have to take that is, you have to take the polynomial set. Over the field of real numbers only I have taken, no, so the constants, that is the scalars have to be taken from the real numbers. So let me take here n plus 1 vectors are there, no, so let me take n plus 1 scalars. So alpha naught, alpha 1, alpha 2, etc. Alpha n belongs to R. Write the linear combination alpha naught plus alpha 1x plus alpha 2 x square plus etc. alpha n x power n. Each one is a vector here. Okay, so I am getting this combination. Look at this, where these alphas are varying over R, real numbers. So for different values of alpha, they will give different polynomials of degree what, less than or equal to n. Suppose this alpha n equal to 0, it give polynomial of degree n minus 1. Okay, so by variating the values of alphas, we will get different polynomials. So this set will generate the set of all polynomials over R of degree less than or equal to n. Okay, so up to this I conclude the span of a set problem. Next I am coming to linearly independent set. In V3 of R, check whether this set of 3 vectors are given are linearly independent. You see, the actual definition is there. What is the actual definition? If you take the linear combination equal to 0, each of the scalars must be 0. That is the actual definition. But I will tell you a shortcut method for checking whether the given set is linearly independent or not. Look at the vectors, 3 vectors, and they are 3 tuples, isn't it? So we can write a 3 by 3 determinant. Write a 3 by 3 determinant and find out the value of the determinant. If it is equal to 0, if the value of the determinant equal to 0, the vectors are linearly dependent. Okay, that means you have studied the properties of determinants, no? If one row is the linear combination of the others, then the value of the determinant will become 0. The same thing I am applying here. When I get this determinant equal to 0, any one of the vectors has a linear combination of the other two. So when you get the determinant value equal to 0, the set is linearly dependent. But this is not applicable for all types of problems. Suppose if I am given with the 4 vectors in 3 tuples, in 4 vectors I am given, means I cannot check with this one. Okay, I have to use some other rule, isn't it? So only for 3 vectors and 3 by 3, either 3 by 3 or 2 by 2. In that case, suppose in V2 of R 2 vectors are given, you can make use. Suppose in V4 of R 4 vectors are given, you can make use of this method. So this is used to check whether the given set is linearly dependent or independent. Determinant equal to 0 implies linearly dependent. Okay, next one more set of vectors I have taken. In V3 of R, I have to check whether it is linearly independent or not. Okay, find out the determinant. Here I am getting the determinant value equal to minus 9. It is not equal to 0. Therefore, the set is linearly independent. Okay, then one more set is given. 1, 2, 3, 2, 3, 1. Only 2 vectors are given, no? So I cannot make use of this method. So I have to go by the definition only. Okay, so what is the definition? Assume the linear combination of these two vectors equal to 0. Okay, alpha 1 into 1, 2, 3 plus alpha 2 into 2, 3, 1 equal to 0. Okay, now simplify this expression. What is the first coordinate? Alpha 1 plus 2 alpha 2. Equate each of the coordinate to 0. Second one is 2 alpha 1 plus 3 alpha 2 equal to 0. 3 alpha 1 plus alpha 2 equal to 0. From the first equation, I am getting alpha 1 equal to minus alpha 2. Put it here. So minus 2 alpha 2 plus 3 alpha 2 equal to 0. That implies alpha 2 equal to 0. So alpha 2 0 means what? Alpha 1 is also 0. So whenever I am assuming the linear combination equal to 0, I am getting the scalars are individually equal to 0. Therefore, this given set is linearly independent. Okay, right. Next one. Check whether this set of vectors is linearly independent or not. So the 3 matrices are given in which one? M2 of R. So let us take the linear combination alpha 1 into the first matrix plus alpha 2 into the second matrix plus alpha 3 into the third matrix equal to 0. Now simplify. The first element is 2 alpha 1. Here are 0. So 2 alpha 1. The second element is 0 0 minus alpha 3. Okay, what is the third element? 0 plus 2 alpha 2 plus 3 alpha 3, and the fourth element is 0 entirely, equal to the right hand side 0 means what? 0 element of the corresponding vector space. So 0 0 0 0. Equate each of the element to 0. So by equating the first element, we say alpha 1 is 0. This one implies alpha 3 equal to 0. If both alpha 1 and alpha 3 are 0, here I am getting alpha 2 is also equal to 0. Therefore, this set is also linearly independent. Okay, next this problem is something different from the previous one. Here, what is the vector space we have? V3 of Z5. That means we have triplets, and the triplets are, the numbers are taken from where? Z5. Z5 means what? 0, 1, 2, 3, 4. Okay. Over this vector space, we have to check whether this is linearly independent or not. So from where I have to choose the scalars? From Z5. Alpha 1, alpha 2, we have to take from Z5. Now let us check alpha 1. Suppose the linear combination equal to 0. What happens? Alpha 1 plus 2 alpha 2 equal to 0. Second, 3 alpha 1 plus alpha 2 equal to 0. Third one is 2 alpha 1 plus 3 alpha 2 equal to 0. Now let me take these two equations, because if I add these two equations, what do I get? 3 alpha 1 plus 2 alpha 1 equal to what? 5 alpha 1. But over Z5 only I am getting no. So 5 alpha 1 means what? It is simply 0. Okay, plus 4 alpha 2. Alpha 2 plus 3 alpha 2 will become 4 alpha 2 equal to 0. This implies my alpha 2 is 0. So if I put alpha 2 equal to 0, what do I get? Alpha 1 is also equal to 0. Therefore, both the scalars are 0. That means the given set is linearly independent. Where? In V3 of Z5. Okay. Then next one is, here I am going to give the dimension and the basis for certain well-known sets. See, already have explained you how to check the span and how to check the linear independency of the sets. So with that one you can check. These are some standard results that you have to remember. Okay, no need to go proceed with the problems. You can directly say for V2 of R, no, this is the basis, that is linearly independent as well as it spans the whole space 1 0 0 1. This forms a basis, therefore dimension equal to 2. In general, for Vn of R, the dimension is equal to n. What is the basis? E1, E2, etc. En. E1 means in the first place only you will be getting 1. Rest of the n places 0. E2 means second place 1. Rest of the things 0. Okay, right. And singleton set 1 is there, no? This is the basis for the vector space R over itself. R is a vector space over itself, no? And its dimension is equal to 1 because only single element is there, no? Okay. And then we know C is a vector space over R. So what is its dimension? 2. What is the basis? 1 comma I. This generate the full set C over R. Okay, and M2 of R. For M2 of R, this is the basis 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 1, and this forms the basis and dimension is equal to 4. Okay, next one is for polynomials. Set of all polynomials, real polynomials of degree less than or equal to n. This is the basis 1x, x square, etc. up to xn. How many elements are there? N plus 1. So the dimension is equal to n plus 1. Okay. See, the next one is generalization of this result for M2 of R. What do you mean by M2 of R? Set of all 2 by 2 matrices with real numbers, isn't it? Set of all 2 by 2 real matrices. In the same way, if you take set of all m by n matrices over any field F, its dimension is m into n. That is number of rows into number of columns. Here 2 by 2 matrices, no? So it is 2 into 2 equal to what? 4. This is the generalization of the fifth result. And this is the 0 vector space and its dimension is 0. Okay, I hope you understand all the problems and results I have discussed in this video. Thank you.